the series of basics of software defined radio techniques and practical applications, we were discussing the linearization techniques of power amplifier. Under this technique, we have earlier covered different type of models. These kind of models such as Saleh model, Raff model, Ghurbani model, you can simply put into a MATLAB or any other tool because they are equation based, and then you can use them instead of power amplifier. By keeping those tools in the any transmitter system, you can actually visualize the effect of power amplifier nonlinearity. Now, after looking at the impact on the signal quality, now let us go into the details of linearization techniques to remove the unwanted effect of power amplifier nonlinearity. So, if you look at this slide, we are showing different transmitter linearization techniques. Basically, there are three types of techniques which are found in literature. One is called feed forward technique, another is called feedback technique, and a third one is called pre-distortion technique. So, we will go through these techniques so that we have idea of the state of the art which is currently available in the market. So, first of all, feed forward technique, which we can see here. The feed forward technique contains two power amplifier. One of the power amplifier is the amplifier which we want to linearize. So, let us say this is our power amplifier which we want to linearize. So, the schematic of feed forward goes something like this. So, basic signal, which is the input signal X, it is applied to power amplifier as well as it is sent through a different path to a parallel branch. In this second branch, you have a attenuator and a phase shifter which controls the amplitude and the phase of this incoming signal, and then these are summed together and second loop starts. In this second loop, again you have attenuator and a phase shifter. In second path also you have a amplifier. And this is the output of this whole system. So, this whole scheme is called feed forward scheme. This is called feed forward because you take the error signal from one path and then you feed it to the second path, and the second part does the second type of correction. So, how does it actually work? You have your input signal here. The first loop is called nulling loop and the second loop is called error cancellation loop. This power amplifier is the amplifier which has highest power. This amplifier which we have to use to linearize this power amplifier is actually having a smaller gain and it does not work into that much higher power level. So, how does it work? We will have a look at this. For example, let us say our input signal X, it is having input power of 20 dBm of each tone. In frequency domain, the signal is between F1 and F2. So, for example, if you are having 2 gigahertz signal at F1, if they have 10 megahertz separation, the second signal will be at 2.010 gigahertz. So, it will be F2 and it will be F1. So, let us say it is 20 dBm is the power of this incoming signal. This actual power amplifier has the gain of 40 dB and of course, it is able to provide you very high power, and when you apply this signal here you will have 20 plus 40. So, almost 60 dBm output you should be able to see here, but actually you will not see 60 dBm exactly, but somewhere around that, let us say 56 dBm, because some of the power is actually going into IMD products. So, your F1, F2 values, and then you will have your IMD terms, third order IMD, fifth order IMD, seventh order IMD, and so on, and then you will have harmonics. So, it is third order, it is fifth order, and it is seventh order. Now, if you remember, we have for solid state power amplifier the formula to calculate the carrier to interference ratio of the third order. It is the formula which we have been using earlier a lot, 20 plus 2 times output power back off. This is the output power back off from the P1 dB point or the saturation point. So, suppose if it is 0, we are not taking any output power back off, then what basically we are saying that for any SSPA, normally the carrier to third order interference level will be 20 dBc below the original power. So, if it is 56, it will be almost 36 dBm power. These are containing almost 36 dBm because of this formula. It is approximate because it is the approximated formula thumb rule for the SSPA. So, this much we can see. Now, what we want actually our signal to have only our amplified signal, and we do not want these signals. So, here we want only F1, F2 component and not other component. So, what does this feed forward scheme does? In the first nulling loop, it removes the original tone and only IMDs are remaining here. So, how do we do that? So, this X which was input was this one 20 dBm power, and after that at the output we had this path. So, what do we do? First of all, we put a attenuator in this path, so that the gain of this path and the gain of this path, they are equal. So, basically if this path, let us say have, because we do not have any gain component here, let us say 10 dB drop is happening because of this resistor in the path and because of this phase shifter, amplitude and phase control unit. So, let us say 10 dB is dropping here. So, gain will be minus 10 dB because it is drop, not the gain. So, negative sign here. Then this coupler which is allowing this signal to come here will have almost, coupler generally will have 3 to 6 dB drop. Again, because it is a analog component, it will have some drop. It can vary from 3 to 6 dB anywhere in between. So, let us assume it is 3 dB loss. So, minus 3 dB. So, then what we will do? We will add the gains of this path and we will decide what should be the attenuation here, so that the gain of these two paths will be equal and we can balance this gain. So, we will check this way and this way. So, let us say I call it anti-clockwise and let us call it clockwise. So, CLK clockwise, if I say see the power here, it will be power of X plus gain of this element which is actually minus, which is actually loss, minus 10, and this is the gain from this path, the output power here from this path. It should be equal to whatever has been added from this path. So, X plus 40, then 3 dB drop because of this coupler, so minus 3, then this attenuation. So, this attenuation which we have to decide, and then whatever power we are getting here, it should be equal. So, Let us compare these two parts and it will be cancelled out and it will come here. So, attenuation will be basically minus 40 minus 10 plus 3. So, minus 50 plus 3 minus 47 dB. So, minus sign suggests that it should be attenuation and not gain. So, this value will be minus 47 dB. When we put it like this, then the gain of this path and this path is equal. What does it mean? It means that we have removed all the gain and attenuation of this path, and now the signal we are receiving at this point is basically the signal at f1 and f2 and this is the signal at 20 dBm, the same power here, because we have removed all the gain, it has received from here and other elements. So, similarly it will become 0 dBm. For third order we are concentrating, and other fifth and seventh terms are even more below here, fifth and seventh. So, now at this point this signal which is coming from here is this one in frequency domain, and the signal which is coming from this path is this signal, right. Now, we set our phase so that phase of clockwise direction and phase of anti-clockwise direction path is 180 degree out of phase. So, we select this phase so that we can make sure that it happens. If this will happen, then these components are at 180 degree out of phase with this component. It means this signal at the output of this point will cancel out these terms, and we will be having only these components with 180 degree out of phase condition. So, at this point in the at the output of first loop we will be having, it is f1 f2, and if this cancellation is perfect, then we will be having only our IMD terms. If our path is only it exactly 180 degree out of phase, then these components will be completely cancelled out and we will not have anything at this point, and only third order, fifth order and seventh order terms will be remaining. Now, that is why we called this first loop nulling loop, because it is nulling the main tone. So, what is remaining now? Only the error, only the IMD terms in the second path. Now comes the second amplifier into picture, and these components, this path, the coupler, it is giving one portion of the this signal into this path and the other portion, main portion, into that path. So, in that path we are still having all these components with a little bit lower power. Let us say 3 dB has been lost here. Now, we are getting the components here at this point, which are f1, f2, and this value will be 53 dB. Why? Because 3 dB has been lost. dB has been lost, and you have other components, they are also lowered by 3 dB. So, third, fifth, seventh, third, fifth and seventh order components here, they are also, which was 36, now it is 33 dBm, 33 dBm, these values. What should be the role of the second path? The aim of this second path is that we add these IMD components to this path, it is the coupler 2, again it will have 3 to 6 dB drop because of the property of this passive element analog component. Then when if we are able to add this to this signal at 180 degree out of phase, then we will actually cancel all the IMD terms, right, all the IMD terms will be cancelled, and at the output we will be able to get our signal only at F1 and F2, and this is what we require. We want to send a signal which is a two-tone signal, and we want to receive a signal which is again a two-tone signal with some gain. So, let us say 53 dBm. Now, how will we achieve this? Again we have to keep in mind that this clockwise direction from here to here, phase 1, and the other phase from here to here, phase 2, in the error cancellation loop should be 180 degree out of phase. So, phi 1 should be phi 2 plus 180 degree or minus 180 degree, so that they are out of phase here, right. So, we will measure the phase of this path, and we will measure the phase of this path, and we will tune this phase so that we can maintain this relation in error cancellation loop, error cancellation loop. It will allow the cancellation of the IMD terms because they are 180 degree out of phase and there is nothing in the in-band signal. So, only this in-band signal will be remaining, although phase will be different, but phase does not matter, that can be compensated later on. So, main requirement is the cancellation of IMD which we are able to get. What is another requirement? Of course, 180 degree out of phase will be help us in cancelling these components, but only when these amplitudes are matched together, right. So, there come this attenuation and this amplifier into picture. That is why, because this is to amplify this IMD terms to this level, right. So, basically we play with this attenuator and amplifier to achieve the same level between these IMD terms here. Now, this amplifier is actually a linear amplifier, it should not introduce its own distortion terms, otherwise whole purpose will be defeated, otherwise it will introduce its own IMD, we do not want that. So, it has to be a linear amplifier. What is the positive point? This amplifier has to amplify IMDs which are much lower, they are almost 20 dB below the main power level, right. So, it was around 0 dBm here. So, we can use low power amplifier here, and we can use easily this to be in the linear region of the power amplifier. So, by doing so we will match the gain of this path, and again the power of these components should be equal to the power of these IMD components, so that the perfect cancellation will happen, okay, and we will get our actual signal output. So, this is the feed forward system. This feed forward system, as you can see, is using two amplifiers to linearize one amplifier. So, this was the main amplifier which we wanted to linearize, and for that which components we had to use? We had to use couplers, we had to use power dividers, okay, I think dividers. We had to use extra linear amplifier, attenuators, phase shifters, so all these components, analog components, are the part of one feed forward network. So, as you can see, these are analog components, all of them are a couplers, power divider, this amplifier, they are analog components and they have their own errors, they are not perfect. So, each of them introduce their own errors. For example, this coupler will have some losses there, those losses have to be calibrated properly. These attenuators has to work very fine tuned way. Why is that? Because in both of the loops you had seen that there is utmost importance that the power level should match. For example, in the first nulling loop, if your powers are not matching for your P output and the signal output, then this tone signal will not be completely cancelled. What you can see some small signal here, right. So, because of this imperfection, you will see this small signals here, and when this path will go and meet with this path, then in turn you will again see some IMD terms here. It will not be completely cancelled, although C by I ratio might be much higher than the previous one, which when it was almost 20 dBc. Now maybe it will be 50 or 60 dBc depending on how perfect your systems are, but because they are the real system, they might not be perfect, and you can see some IMD terms here. Moreover, in the first path, if you had some tones remaining here and this tone will go here and add with 180 degree with the signal which is coming from the other path, then because they are matching at 180 degree, this power will drop because it will be subtracted from there. So, maybe you will get only 51 dBm. So, you are losing 2 dBm gain in the main power. So, imperfection of these components is one of the hindrance. Then first limitation. Second limitation, we are using such a bulky scheme here, so it is costly to purchase all this and then to make this system. It is complex and not portable. Once you make this arrangement, or you do not want to shift anything, you do not want to change anything, because even this cables, they should be calibrated, everything should be calibrated. It is not a portable solution, it is a complex solution. And the fourth one, the efficiency of this system will be very low. Why is that? If you remember, efficiency was given by P output in the RF domain divided by P DC. So, output power is decided by the signal we are receiving here, right. So, the summation of these two tones, that will be our output power, and PDC is the DC power consumed by the power amplifier. But in this case, our PDC is not only consumed by this power amplifier, it is also being consumed by this another amplifier, and this amplifier is not giving us any gain, it is just helping in cancelling these extra IMD terms. So, the P output RF power is same, but the PDC becomes PDC1 plus PDC2. So, of course, this denominator power is increasing and efficiency is going down. So, low efficiency. Now, these are the limitations. What are pros here? Very wideband solution, because this power amplifier it is limited only by the bandwidth of such components, phase shifters, your attenuators, your couplers, and this amplifier. The passive elements are mostly very wideband, they do not give us much trouble, but this amplifier has to be broadband, and if it is broadband, then it can give you very wideband solution. So, it was a very wideband solution, so it has been used for even more than 2 bands. It has been very popular for the implementation in the base station, when you can use the bulkier size solution also, but maybe not for the mobile, because it will take space. It is very wideband, and C by I correction is high, because if you can have these components very C by I3, because third order is mostly higher, So, basically if you are able to get this tuning properly done even in manually, you can achieve very high level of C by I ratio, because the IMD correction path is independent of the actual signal processing path. So, these are two positive points and these are the limitation. These limitations they call for other techniques, and this is how we go to the next technique, which is feedback technique. So, as you can see here, this is our power amplifier and we are using one feedback. This feedback will contain time delay element. So, let us have a look there. So, feed forward had a big problem that it was not portable and it was complex and costly because it was using many components. So, feedback technique is a solution to that. So, in this technique, basically this is your power amplifier and we see that distortion is occurring at the output power amplifier output. So, suppose these are the input signals at F1, F2 and these are the IMD components at the output. So, instead of using feed forward, we simply take some portion of this sample at the feedback and with some phase and amplitude correction, we apply the signal back here. So, this output signal it contains IMD terms as well as main tones. So, when you get it back, we design our feedback circuit in a way that we will remove the effect of main signal here, delay should be compensated, so that whenever we are applying the signal here, we are able to get the signal at the same instant when it is being applied or nearby, because if our system is not changing very fast, then this PA will have almost same property for nearby signals. So, for example, with T, if this is your system is signal at the PA and we are working very near to signals, then it is almost the error is very small. So, it almost excites PA in a same way. So, as long as signal is continuous, there is no sudden jump. This assumption it holds, and because of that, this is VT amplitude I was talking about. So, because of that, as long as you are able to compensate for tau in a reasonable manner and you play with the phase and amplitude, then we can control this IMD performance a little bit, and because you can see this same elements which we were using in a feed forward, they are being used only once in one feedback, then it is a very portable solution and it is less costly solution as compared to feed forward solution. Again, limitations here, advantage is very clear, but limitations, main limitation is stability. Whenever we are talking about any feedback solution and from the control theory, you might know that we have to take into account the stability. The system can go unstable for particular jitters, for particular excitation, it might lose its stable position. So, stability is one of the concern, because input fluctuation jitters cannot always be controlled. So, one main concern stability. The second one is limited bandwidth. So, what is this limited bandwidth? Because we are dealing with a system which is time delayed version here, right. So, if from your DFT formula, if you, because you are dealing in the discrete domain, if you remember, if we do something a shift of D delay in discrete time domain, then it appears in the frequency domain in this way. So, it is your frequency domain representation of xn TFT, IDFT, and it is its frequency domain representation at the present instance. But when a signal is coming from a delay, then it appears as a function in frequency domain, a component in the frequency domain. So, we cannot go to higher bandwidth because those bandwidth will be representing actually a delayed signal here. So, they will interfere with each other. So, if it is a single carrier signal, it is okay because this kind of components will be falling nearby the actual tone, but if it is a bandwidth signal, then we will have distortion components which will be interfering with this. So, because now we are going for the very higher bandwidth signals when we are moving from 3G, 4G towards 5G. So, this feedback scheme is not that good scheme, especially when we want to have a system which will keep working continuously. There might be jitters, there might be other effects which we cannot control, effect of atmosphere, temperature, etc. So, it is not a very reliable solution, although it is very portable solution. So, what can be the compromise between these two? And here comes the pre-distortion technique. Pre-distortion technique is kind of combination of feed forward and the feedback technique. In the feed forward technique, if you remember, we were removing the distortion term and then we were deducting them at the outer loop. Now, in the pre-distortion technique, we put that element which is introducing the IMD terms before our power amplifier. So, this is the scheme where instead of using in the feedback, we can put something before your power amplifier, and it contains the property of these two. So, this pre-distortion is something we are going to discuss in detail because it is inherent part of digital signal processing techniques which can be used in software defined radios. So, we will be discussing it in the next lecture. Thank you.